This video is a continuation of our lesson on section 5.8. Sorry, 5.9. 5.9 was approximate integration. We've already covered the trapezoid rule, the midpoint rule, and the error bounds associated with each of those. In this video, I'm going to talk about Simpson's rule and cover that and its error bounds, and that will complete our lesson on section 5.9. Simpson's rule is our fifth technique, if you want to think about it that way. Right-hand endpoints, left-hand endpoints, midpoint rule, trapezoid rule. It's our fifth technique for approximating an integral. And the idea behind Simpson's rule versus the other four is Simpson's rule says, let's just take 3 points. And Simpson's rule says that through 3 points, there is a distinct parabola, right? There's a distinct parabola that will pass through these points. So if we have 3 points, we can find a distinct parabola that will go through those 3 points. So instead of taking our partitions of our function and thinking about x sub 1 and x sub 2 and x sub 0, and instead of thinking about using these 2 points and maybe, for example, left-hand endpoints, we're going to use 3 points with Simpson's rule. We're going to use x sub 0, x sub 1, and x sub 2. We're going to take these points here. We're going to use those as our 3 points that determine a parabola. Now, I'm going to do a quick development of Simpson's rule, just so we know it doesn't come out of thin air. It's not just a formula that shows up in a box. And what we'll do is we'll choose our points. Well, we'll choose them nicely. We'll say that these x values are h and negative h. This is 0. And so this is the point h y sub 2. This is the point 0 y sub 1. And this is the point negative h y sub 0. And so this will be our x sub 0. This will be our x sub 1. This will be our x sub 2 when we generalize Simpson's rule. So what do we know about parabolas? Well, we know if we want to find the area under this parabola, right? Because that's what we're looking for. That's our approximation. Our approximation now, instead of being a rectangle, is going to be the area under this parabola. That's going to be the integral from negative h to h of whatever this parabola is. And that parabola in general is ax squared plus bx plus c dx. But if we take a look at this closely and we consider a couple of facts about our parabola in its current orientation, so that we have this uniformity between the positive x and the negative x. Now, if we simplify this, we can rewrite this as the integral from negative h to h of ax squared plus c. And this isn't going to seem like one of those things that maybe we would have thought of off the top of our head, but like so many developments, there's an aha step in here. And that's what I call them. I call them aha steps. This function is even. That's a squared, that's a 0. So this is x to the 0, x to the 0, x squared. This is even. This function is symmetric with respect to the x-axis. This function is odd. And we have theorems that tell us if we have an odd function and we integrate between negative h and h, or negative a, and the function is odd, in other words, it has origin symmetry, and this function is odd because the power on x is 1, this integral right here is going to equal 0. And this integral, because this function is even, we can find this by taking 2 times the integral from 0 to h of our function. Now, if we integrate that, right, if we do that integral, we know what that's going to be. We integrate this. This is going to be 2 times, and we're going to have ax cubed over 3 plus cx. And we're going to evaluate that between 0 and h. Well, if we plug 0 in for x or 0 in for x cubed, we're going to get 0. So this is going to simplify to, when we get all done, 2 times, and that's going to be a h cubed over 3 plus, and this is going to be c times h. Now again, when we plug in 0, we're going to get 0, all right? So this is our answer to this integral. Now, I'm going to factor out a 3 because I don't like this fraction. So when I factor out a 3, that's going to turn this into a 6, right? I'm going to multiply through by 3, factor out a third, whatever you want to think about it as. So if I do that, I'm going to pull the 3 out, and I'm going to get h. I'm going to pull out the common factor of h. I'm going to get h over 3 times. Here I pulled out the factor of 3. I still have the 2, so I have 2 times a h squared. Here I have plus. Now I still have a factor of 2, 2 times c, but I factored out a 1/3, so I have to multiply this by 3. So I'm going to get a 6c here, and we're going to put a star next to this because we're going to use this formula in our development. So now we're going to take these 3 points and we're going to plug them into the general formula for the parabola. So we know that y naught, right, y naught right here is equal to a times its x value squared plus b times its x value plus the constant c. Now, if we simplify that, of course, negative h squared is ah squared. This is minus bh plus c. So y naught is equal to this. Y sub 1, well, y sub 1, x is 0. So when we plug this in, we're going to get a times 0 squared plus b times 0 plus c. And that gets us just c. So y sub 1 is equal to c. What about y sub 2? Well, y sub 2 is equal to, and if we plug that in, we're going to get a y sub 2 h. So we're going to get h squared plus bh plus c. Now, if we add all these together, right? If we add these together, we're going to get ah squared plus ah squared. On the left-hand side, we're going to have y naught plus y sub 1 plus y sub 2. If we add them together, we're going to get 2ah squared. That's a minus bh, that's a plus bh. Those go away. And we get c plus c. That's 2c. Now, if we look back over here, we have 2ah squared plus 6c. Here we have 2ah squared plus 2c. So instead of just taking one y naught, which gave us 1c, plus 1c plus 1c, so when we added them together, we got C plus C plus C. I'm not very good at adding, apparently. I had 2 there, but we have 3. So if we look at this, right, if we look at this expression, and if we decide to do something really shocking, if we look at this part inside, 2AH squared plus 3C, here we have 2AH squared plus 6C. If we would take another y sub 1, that would give me another C. That would give me the 4C. If I would take a third y sub 1, that would give me C, C, 3 C's, 5 C's. But if I would take instead 4 y sub 1s, that would give me 4C. And then I would be able to write this, instead of writing this, I would be able to put in 4 y sub 1s, and I would get this, 2AH squared, right? That's that AH squared plus that AH squared, 2 of those. We still have negative BH here plus BH here, that's 0. But now we have C, 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 but that's 4 C's, we get plus 6C. Well, that's this right here. So where are we going with this? What are we trying to do? Let's not lose sight of the fact that we're trying to find the area under here. And we did that with this integral, which we then wrote out this way, which was intuitive? No, not at all. But which did help us, because then we could use our integration rule from negative a to a, even, multiply by 2 and go from 0. Odd equals 0, and we integrated and we got this. This is our formula for the area under the parabola. But now we have another expression right here for 2AH squared plus C. We have another expression for 2AH squared plus 6C. So what we can say now is the area under our parabola here is equal to this. But we can rewrite that as h over 3 times, instead of 2AH squared plus 6C, why not, plus 4 y sub 1s plus y sub 2. Now from here, we're going to observe that there was nothing important about this x sub 0, this x sub 1, and this x sub 2. In general, if we take any 3 points, such as those, and we do this development, we're going to get this same formula. We're going to be able to say, if we went from x sub 2 to x sub 3 to x sub 4, because that would be our next parabolic arc. If we went from x sub 2 to x sub 3 to x sub 4, our area there, we'll write it in pink, would be h over 3. Our left-hand endpoint would be y sub 2. That would be going along with this. But then here we would have 4 y sub 3s, and then we would have 1 y sub 4. Exactly the structure we have right here. Well, if we take a look at what we have here, we could continue this and continue this and continue this for each of our partitions. And if we did that, what we would see then is to find the total area, of course, we would want to add all these sub areas together. And if we did that, everybody would have a factor of h sub 3. All right, there would be an h sub 3 in front of h over 3 here and h over 3 here. And what would we get? We would get something that looks like this. The area is equal to h over 3 times. Now we only have 1 y sub 0, so we'll get that. We'll put that right here. We have 4 y sub 1s. But look, we have 2 y sub 2s. Now, here we have 1 y sub 4, but our next partition would be y sub 4, y sub 5, and y sub 6, right? That would be our next partition. Would be, it would start at y sub 4. Here we ended at y sub 2. We started at y sub 2. It would start at y sub 4. So it would end at y sub 4. So our next partition, if we were to write it down, right, I'll just jot it down in another color, throw it over here. Our next partition would be, the area is h over 3. We would start at y sub 4. We would get 4 y sub 5s, and then we would get a y sub 6. And so when we add these all together, we have our y sub 0, our 4 y sub 1s, our 2 y sub 2s, our 4 y sub 3s. Now we're going to have 2 y sub 4s. And we're going to have 4 y sub 5s. And we're going to have 2 y sub 6s. And this would just continue until we finally got to the end, when we got to our last point, which would be, we would have 4 y sub n minus 1s, and we would have y sub n. This formula right here is what we know as Simpson's rule. This tells us how to find the area. And so we can use this, right? We can use this as our formula for approximate integration. Now we have to put some conditions on here. H is equal to our partition, so that's b minus a over n. Now in our book, we use delta x. In my little development right here, I just used h. I never really went back and called it delta x, but that's our delta x. And n must be even. So if you want to use Simpson's rule, remember, this is your choice, right? You're the one who has to figure out the approximate value of the integral. So if you're going to use Simpson's rule to do that, you're in charge. You're going to choose an even n, because if you don't choose an even n, Simpson's rule doesn't work. We need pairs of partitions, right? When we go back, we went from y sub 0, sorry, from x sub 0 to x sub 1 to x sub 2. So we needed a pair. And then we go from x sub 2 to x sub 3, x sub 3 to x sub 4. We need a pair. So n must be even. Otherwise, the layout doesn't work. Now, this is the traditional way you write Simpson's rule. Some people have no trouble with this. They're like, well, you know, the odds all get a 4. The evens all get a 2. The end points are there's just one of those. And for a lot of us, that's good enough. Now, if you prefer, and it's not required, but another way you can think about this is you can think about it as the area is equal to h over 3 or delta x over 3, whatever you want to call it, y sub 0 plus 4 times, and then you put your odd y values here. And now when I say odd y values, I mean the odd subscripts, right? Your odd subscripts. So this would be your y sub 1, your y sub 3, your y sub 5s. And then you get plus 2 times your even y values here. And I'm going to put quotes around this odd and quotes around this even to make sure we understand that that's referring to just the subscripts, not the actual value of the y value. And then we get plus y simple. So whichever of these two versions of Simpson's rule you like, you can use. We're not worried about where it comes from. We're just worried about using it. So this is our formula, one of these two, the black formula or the pink formula. That's our formula for Simpson's rule. Now, we have an error-bound formula for Simpson's rule as well. I'm not going to develop that. I'm just going to write it down. It's worthy to note that Simpson's rule is more accurate than the trapezoid or the midpoint rule. Right? We wouldn't be concluding our discussion of approximate integration if we were going to give you the fifth method and say, oh yeah, and by the way, it's the worst one of all of them. So what's the formula for the error bound for Simpson's rule? Well, the error bound for Simpson's rule is very similar to the error bound we used for the trapezoid rule and the midpoint rule. When you look at it, it says suppose, and there's an absolute value, and we're less than or equal to k, and this is going to be a derivative again. But instead of being the second derivative, it's the fourth derivative. Okay. So k is some number that bounds the fourth derivative within our interval. And it says then that if E sub s, E sub t trapezoid rule, E sub n error for midpoint rule, and error for trapezoid, E sub s error for Simpson's rule is the error when using Simpson's rule, then we know that error is going to be less than or equal to k, the same k we found before, except remember this is the fourth derivative. Again, we have b minus a, but now instead of being to the third power, it's to the fifth power, okay? This was the second derivative before, this was the third power before, so it's one higher than the derivative. Same pattern here. We have the fourth derivative here, we have the fifth power here. And now in the denominator, our constant, instead of being 12 or 24, is 180, and then we have n to the fourth instead of n squared. All right. In the previous versions of the errors for the trapezoid rule and the midpoint rule, this was the second derivative, this was squared. Now it's the fourth derivative, this is to the fourth power, right? This is how we keep this straight. If we can just remember this is the fourth derivative, we know this has to be the fourth power because they match. If we can keep straight this is the fourth derivative, then we know this is the fifth power because the power on b minus a is always one more than the derivative we're taking to find our value of k. All right, so that's Simpson's rule. I'll do a problem from the homework where I work out Simpson's rule in my homework solutions video. All right.